Why does ice float? Not just as a fun fact, not as a trivia night curiosity, but as a hinge in the door between a living Earth and a silent one. Why does the solid form of our most familiar liquid refuse to sink like almost every other solid does in its own melt? And how did that single quirk save life on this planet? If that seems like a small oddity, consider this: your heartbeat, your memories, and the climate outside your window are all stabilized by the same invisible network threading through a glass of water. So, tonight, we ask a deceptively simple question, and we let it lead us to the edge of what we know and what we suspect. What is water, really, and why does it break the rules of nature? To start, let's meet the protagonist, a molecule small enough to hide in a sigh, but powerful enough to scaffold the biosphere. 2 hydrogens and 1 oxygen, H2O. But not a straight line, more like a bent elbow, the hydrogen atoms angled about 104.5 degrees apart. That bent shape matters because it makes the molecule polarized, like a tiny battery with a slightly negative side near the oxygen and slightly positive sides near the hydrogens. Polar means that charges are unevenly distributed. If you picture molecules as little faces, water's face is a smirk, one side hoarding electrons, the other side hungry for them. And because of that smirk, water does something extraordinary. It forms connections, a network called hydrogen bonds. A hydrogen bond is a handshake between molecules, not as tight as a full chemical bond, more like a magnet clasp that's strong in a crowd. A single hydrogen bond is relatively weak, a few % of the strength of a covalent bond, but collectively they become a social force. Water molecules are social creatures. They hold and let go in a constant square dance, grab, spin, release, grab, on the time scale of a trillionth of a second. That's a picosecond. Blink, and millions of entire networks have formed and dissolved within the blink. This ceaseless jitter becomes the stage on which life performs. Here's where water starts violating expectations. Most substances get denser when they freeze. Think of people huddling together as it gets cold. But water does something mischievous. As it cools from room temperature, it gets denser, down to about 4 degrees Celsius. That's the point of maximum density. Below that, as it approaches freezing, it actually expands a bit. When it freezes, it locks into a lattice, a hexagonal crystal with empty spaces like scaffolding, which makes ice less dense than liquid water. So ice floats. And not just as a novelty. Floating ice forms an insulating lid over lakes and oceans in winter, keeping the liquid below from freezing solid. Under that floating lid, fish swim, ecosystems nap instead of perish, and spring comes back to a living world. That's quirk number 1. But water is a portfolio of quirks. It has a high heat capacity, about 4.18 joules per gram per degree Celsius at room temperature. In human language, that means it's stubborn about changing temperature. Imagine a friend who refuses to get angry quickly and refuses to cool down rapidly after an argument. Water takes a lot of heat before it warms up, and it gives up a lot of heat before it cools down. That stubbornness stabilizes climates. The oceans are planetary thermal batteries. They absorb sunlight in summer without boiling over, and they give it back in winter without collapsing into cold. Your body leans on the same property. You are more than half water, and that high heat capacity buffers your internal temperature against the chaos of your environment. You can walk through a gust of wind or into the shade, and the soup of enzymes that is you keeps simmering at a nearly constant temperature. Then there's water's heat of vaporization, the energy required to turn liquid water into vapor. It's enormous, around 40.7 kilojoules per mole. This is what makes sweating such powerful cooling. When a bead of sweat evaporates, it doesn't politely disappear, it steals heat as payment for the escape. That stolen heat leaves your skin cooler. Global weather is scaled up sweating. Evaporation from the ocean stores energy in water vapor, which releases it when clouds rain, driving storms and redistributing heat around the planet. Water's surface tension is another lever on life, around 72 millinewtons per meter at room temperature. Think of it as the tautness of a trampoline stretched across every puddle. That tautness allows insects to skate on ponds and helps pull water up thin capillaries in soils and plants. It's balanced in our lungs by surfactants. Too much tension and your alveoli would collapse like cling film. And let's not forget water's high dielectric constant, about 80 at room temperature. Dielectric constant is a measure of how well a material muffles the quarrels between charged particles. In air, 2 ions argue loudly, refusing to come together. In water, the crowd of polar molecules interposes and hushes the fight, making it easier for salts to dissolve and for ions to navigate. Even the self-ionization of water, its tendency to split into hydronium, H3O+, and hydroxide, OH-, ions, is a quiet current under our chemistry. Pure water contains far fewer ions than salt water, but its baseline autoprotolysis sets the pH scales 0 at 7 and defines the game board on which acid-base reactions are played. If pH is the tuning fork for the chemistry of life, water is the hand that holds it. We're not just in lecture mode. We're following threads because they go somewhere, into us. In biology, a phenomenon called the hydrophobic effect is the quiet architect that builds cells. Hydrophobic means water-fearing, but truly it's water that dislikes being disordered by oily intruders. Imagine water as a crowd that loves to hold hands in a certain rhythm. Toss a greasy ball into the crowd, and the people at the boundary must reorganize awkwardly. Water doesn't enjoy that. So it nudges the greasy molecules to huddle together, minimizing disruption. That nudge is what drives oil droplets to merge. More importantly, it compacts proteins into their functional shapes and causes lipid molecules, the amphiphiles with a water-loving head and a water-fearing tail, to assemble into membranes. Every cell you've ever had was sketched by water's preference for its own dance. Enzymes, life's catalysts, exploit this. Their active sites are tiny amphitheaters where water is choreographed. Sometimes it's excluded entirely to push molecules together, sometimes it's locked in place as a relay team passing protons. Those relays are part of something called the Grotthuss mechanism, a beautiful trick of physics and chemistry. Instead of a proton physically crawling across a room like a tired tourist, it hops by borrowing handholds along hydrogen-bonded wires. Think of a line of people passing a note. The note moves faster than any single person could walk. In water, protons move faster than you'd expect by ordinary diffusion because they tunnel along networks of hydrogen bonds. It's why acid-base chemistry is so swift in water, why your cells can shuttle charges with such speed, and why the conventional picture of a proton as a marble rolling through a pool is wrong. Now zoom out to materials. Water doesn't have a single ice, it has dozens. Under different pressures and temperatures, the H2O network freezes into many crystalline personalities, hexagonal ice that falls from your sky, cubic ice, and high-pressure ices like 7 and X that lace the interiors of icy moons and exoplanets. There's even supercritical water, above 374 degrees Celsius and about 22 megapascals, where it's neither a regular liquid nor a gas but something in between. In that realm, water dissolves oils it would normally ignore and behaves like a shapeshifter, an underworld river in planetary interiors and industrial reactors. Water can also withstand tension, negative pressure. That sounds like science fiction. How can a liquid be under tension? Picture a rope pulled taut. If it were water, it would be ready to snap with bubbles. In the xylem of trees, columns of water are pulled upward tens of meters by evaporation from leaves, transpiration. The column is under tension, like a glass siphon stretched by the atmosphere and the sun. Trees move water against gravity without a pump, exploiting water's tensile strength. The theoretical tensile strength of pure water is huge, over 100 megapascals, but in real, messy life, impurities and rough surfaces seed cavitation, the birth of vapor bubbles that break the column. Yet, for the most part, it holds. Whole forests are hydraulic machines running on sunlight and the cohesive force of hydrogen bonds. So far, we've toured the highlights. Density maximum at 4 degrees Celsius, ice that floats, a heat capacity that steadies climates and bodies, a vaporization heat that air conditions planets, a surface tension that sculpts leaves and lungs, a dielectric constant that dissolves rocks into ions, a self-ionization that sets the stage for pH, a hydrophobic effect that folds proteins and assembles membranes, proton highways that accelerate charge. Each of these seems like a separate quirk. But scientists have cataloged more than 70 anomalies of water, 70 places where it defies trend lines drawn from other liquids. This is not a bag of coins with odd dates, it's a portrait of an organism with a grammar. Which raises a deeper question: are these oddities symptoms of a deeper organizing principle? This is where we approach the edge, the frontiers where models blur and experiments duck behind rapid crystallization. In the supercooled regime, where water remains liquid below its normal freezing point, evidence hints at a two-liquid story, a fragile, low-density liquid with open, tetrahedral structure, and a high-density liquid that's more disordered, more crowded. Imagine a city that at night can flip between two versions, one with spacious avenues and quiet parks, another with tangled alleys and stacked apartments. The two-liquid hypothesis suggests there might be a hidden critical point, a specific temperature and pressure where these two liquid styles become indistinguishable. But this critical point could be hiding in what researchers call no man's land, a treacherous region of temperature where water crystallizes too quickly for us to measure its liquid behavior directly. We peer through ultra-fast experiments and tiny jets of water, glimpsing what might be a phase boundary in a place our instruments struggle to linger. Why would two liquid personalities matter? Because the balance between open, tetrahedral order and squashed, disordered structure underlies many anomalies: the density maximum, the compressibility, the heat capacity. It would be like finding the common ancestor of many traits. If there's a hidden critical point, then fluctuations between these two structures would ripple through liquid water even at ordinary temperatures, lending it a kind of microstructural restlessness that makes it so good at cradling life's chemistry. But water's complexity isn't only structural. There's a quantum shimmer at the edges. Nuclear quantum effects, not electrons this time, but the nuclei themselves, matter because hydrogen is light. A proton is not a classical point. At room temperature in a hydrogen bond, it blurs. It can tunnel, influencing bond lengths and strengths and the shape of the molecular energy landscape. Swap hydrogen for deuterium, heavy water, where each hydrogen has a neutron hitchhiker, and you change the tune of the whole network. Heavy water tastes like water, but it boils at a slightly higher temperature, freezes at a slightly higher one, and it slows life down. In large amounts, it's toxic, not because of some mysterious radiation, but because the delicate dances of enzymes and hydrogen bonds are tuned to ordinary hydrogen's quantum wiggle. There are other strangenesses. Interfacial water, the water that lives right next to proteins, membranes, DNA, acts differently from bulk water. It reorients more slowly. It sometimes settles into layered arrangements, like a crowd quieting when it enters a cathedral. Its viscosity is different. Its capacity to pass protons or reorganize hydrogen bonds shifts. Life appears to exploit this, tuning water's local behavior to favor certain reactions or structures. In that view, biology isn't just chemistry happening in water, it's the art of sculpting water's microphases, of placing a hydrophobic patch here, a charged group there, to coax water into being a collaborator. Let's test our model with a thought experiment. Swap out water for ammonia. Ammonia is polar too, it can hydrogen bond, and it's liquid over a reasonable temperature range. Could life happen? Perhaps, but consider the hydrophobic effect, it's weaker in ammonia. Membranes might be less robust, proteins less likely to fold into precise shapes. Ammonia's dielectric constant is lower, ions squabble harder, making charge separations more expensive. Its heat capacity is lower, climates would swing more wildly. Now try methane. Titan has methane lakes. But methane is nonpolar, which makes it terrible at dissolving ions and at stabilizing the charges that shuttle through biochemistry. Proton hopping? No highways there. The same logic holds. If you try to write the opera of life in a different solvent, you may find the choir can't reach the notes. And that floating ice? In methane, solid methane sinks in liquid methane. Imagine ecosystems in a lake where winter coats the surface with heavy ice that sinks and stirs the whole volume, freezing it solid from the bottom up. Imagine no insulated refuge below a floating lid. Life might still find a way, but the energy budget would be punishing, the buffer thin. This is the reality model stress test. If water were normal, complexity would be expensive. With water's rule breaking, complexity becomes affordable. Its high heat capacity and enormous vaporization heat smooth the energy landscape of climates and bodies. Its dielectric constant and hydrogen bond agility allow ions to navigate, charges to separate and recombine, proton wires to form. Its hydrophobic effect makes shape a habit, proteins folding, membranes sealing. Its floating solid preserves pockets of liquid stability through cold seasons. Water hacks the difficulty curve of complexity. Let's slow down and look at something nearly invisible, the lifespan of a hydrogen bond, about a picosecond, versus the timescales of life. Your neurons fire every few milliseconds, your heart beats once per second. Hydrogen bonds in your brain's fluid are made and unmade a trillion times in the interval of a thought, and yet patterns persist. The remarkable thing about the water network is that it is always dissolving and always present. It's like a city where every street is rebuilt every second, and yet traffic never stops. Consider memory. We often picture proteins and synapses as the hardware of recall. It's true. But the ionic currents that encode your memories depend on the way water shields and reveals charges, the way it lets protons leap, the way it tolerates and then releases heat. When you remember a face, water is helping you remember, by being the medium that makes charge flow gentle and precise. Or consider your sense of self. The continuity you feel is partly the steadiness of the chemical reactions in your body, the near constant temperature, pH, and salinity maintained inside your cells. That stability is water's doing, its heat capacity, its willingness to dissolve and buffer acids and bases, its refusal to freeze your organs with every cold wind. The self is built on a platform water holds steady. Now back to the grand scale. Water is not a passive background. It is an active thermodynamic device. When sunlight pours into the ocean, it loads a thermal flywheel. When winds blow over that ocean, water beads from its skin and flies into the air as vapor, carrying heat with it, shaping the engine of storms. When those clouds release rain, the stored energy is returned in a burst that lifts air, drives winds, sculpts pressure fields. Weather is a heat engine, and water is the working fluid that makes it efficient. What about the cosmic search for life? We often say, follow the water. But the deeper principle is follow the right liquid physics. We should look for solvents that can moderate heat, support floating solids to insulate ecosystems, enable fast proton or charge transport, fold molecules into stable shapes, and dissolve salts while restraining their quarrels. Water is one brilliant solution, tuned by quantum effects and geometry, but there might be others. The criteria are not just about being liquid, they are about being a good dance partner for complexity. Let's circle back to the odd fact that water's dielectric constant is so high. It means water hushes charged arguments so effectively that ions, like sodium and chloride, can drift apart and stay apart, stabilized by a cloud of oriented water molecules. The technical phrase is hydration shell, but you can imagine it as a company of tiny compass needles swinging to face charges, forming a coat that lowers the cost of being charged. That coat is dynamic, remade every picosecond, yet it does the job. Without this constant reorganizing, nerves wouldn't signal well, ADP wouldn't be so easy to hydrolyze, and the choreography of metabolism would stumble. Surface tension pulls water up thin tubes, but capillarity alone can't lift water to the crown of a redwood. The cohesion tension theory, another dance step, says that as water evaporates from the leaf, it pulls on the column below, using the strength of hydrogen bond networks to transmit the yank, like a rope made of invisible magnets. Cavitation, a bubble forming when the rope snaps, is a risk. Trees have evolved pit membranes and networked vessels to isolate and bypass embolisms. Nature's engineers manage water's quirks to build skyscraper-scale plumbing systems without moving parts. Sometimes the frontier is under our noses. Pour water into a hydrophobic nanopore, and it behaves like a different species. Confined water can freeze or thaw at temperatures that would surprise you. It can line up into single-file chains, where protons zip along even faster, like a single-lane highway without passing. Proteins with narrow channels use this to move protons and water molecules in and out with near-perfect efficiency, timing chemistry with the precision of a music box. Membranes exploit these microworlds to create gradients, of protons, of ions, that are life's currencies. Let's step into no man's land, the region of supercooled water where it becomes so eager to crystallize that measuring its liquid behavior is like trying to interview a person mid-dance as they spin into a different form. Ultra-short lasers, microdroplets, and jets have shown hints of a transition between two liquid personalities. Heat capacity spikes suggest a critical-like phenomenon. If confirmed, this two-liquid picture could unify multiple anomalies. But science is patient. We don't declare victory on a whisper. We collect, we replicate, we stress test our assumptions. Quantum touches again here. If the proton cloud shifts the balance between hydrogen bond donors and acceptors, then heavy water should tilt the equilibrium differently than ordinary water. Experiments do find subtle changes, melting points, diffusion rates, reaction kinetics. In ice, proton tunneling can flip the orientation of water molecules, exploring configurations governed by ice rules, a kind of local bookkeeping for how hydrogens arrange themselves. Even the exact positions of protons in a hydrogen bond can draw or erase energy barriers. Water is a quantum machine at room temperature, but not in the way of superconductors. It's a device tuned by light atom behavior and collective motion. If all of this feels like a love letter to an ordinary liquid, it is, and it's also a realization that the ordinary is engineered. We live in a world where the most common liquid on our planet is not a bland solvent but an active participant in the geometry of life. Biology is water's playbook written in carbon. This doesn't make carbon unimportant, it makes water a co-author. Look at a protein, carbon skeleton, oxygen and nitrogen decorations, side chains that flirt with or fend off water. But it's water that decides which flirtations become marriages. There's a poem in the fact that the same physics that lets water climb a tree feeds the thunder that waters that tree. Water organizes into hydrogen-bonded networks that hold tension like guitar strings, and it also vacates the ocean, hauling off latent heat to fuel storms. The same properties that fold proteins fold weather fronts. Let's run another stress test. Imagine draining the world of water and replacing it with a generic, normal liquid, one with a lower dielectric constant, a smaller heat capacity, no floating solid, and no proton highways. In that world, climates swing from scorching to freezing with each season, life's internal chemistries drift more wildly, membranes struggle to self-assemble, and enzymes lose the quicksilver of proton transfers. Complexity still might emerge, but it would be fragile, spending most of its energy surviving rather than exploring complexity. That's the cost we don't pay because water picks up the tab. Here's the awe: a glass of water is a vast machine. It holds microsecond storms as hydrogen bonds reorganize. It cradles quantum tremors as protons blur and hop. It carpenters the folding of molecular origami. It carries the seeds of lightning as vapor that climbs and condenses. When you lift it to your lips, you are holding the same network that steadies climates and stitches trees to the sky. You might have heard that water is weird. But weird is the wrong word. Weird implies deviation without purpose. Water's deviations are the purpose. The density maximum at 4 degrees Celsius means lakes overturn in spring and fall, bringing oxygen to depths and nutrients to surface. Ice floating means winter is a veil, not a guillotine. The high heat capacity means coastlines cradle cities and climates. The dielectric constant means mountains dissolve slowly into rivers that feed our fields. The self-ionization sets pH, the language of enzymes. The hydrophobic effect writes the grammar of folding. The Grotthuss mechanism electrifies metabolism. Let's translate a couple more jargons, because jargon hides poetry. Entropy, often cast as disorder, is really the number of ways things can be arranged. Water's hydrophobic effect is partly about entropy. Water prefers to have many ways to arrange itself. Oily intruders force water to align more rigidly at their surfaces, reducing its options. By pushing those intruders together, water earns back options, entropy rises, and the world breathes easier. Another term, critical point. It's where the distinction between two phases vanishes, like fog becoming air without a line. If water hides a liquid critical point, then what we call anomalies might be its whispers at room temperature, echoes of a drama hidden behind a curtain. There's a temptation to ask, did life evolve because water had these properties? Or did water shape life because it was the only path? Both ways of asking are mirrors. Both reflect the truth that evolution navigates the landscape it finds. Water was the landscape, a medium with a peculiar combination of chemical generosity and physical discipline. It allowed molecules to skitter and collide, to separate and join, to fold and unfurl, without too often breaking. It allowed energy to flow steadily enough for complexity to build. Here's another thought experiment for your pocket. Picture snow falling on a primordial ocean 3 billion years ago. If ice sank, that ocean would churn. Cold, dense ice would drag heat down, perhaps freezing the depths before life could get a foothold. With ice floating, a newborn winter becomes an insulating blanket. Beneath the ice, chemistry has continuity, uninterrupted time to think, to assemble, to experiment. Life's earliest labs may have been tide pools protected by winter lids. The more we learn, the more water feels like a negotiated truce between competing tendencies: order and motion, stability and variability. Its tetrahedral geometry pushes it toward open structures. Thermal motion squashes them. Quantum blur gives it flexibility. Geometry restrains it. That tension generates anomalies. And those anomalies, those violations of normal, are the openings through which life climbs. Let's keep pushing our model. Why should water's heat capacity be so high? Partly because much of the heat you add goes into rearranging hydrogen bonds rather than jiggling molecules faster. It's like paying actors to rehearse new choreography rather than to shout louder. This means that water can store energy subtly, As it warms, it doesn't simply speed up, it changes its network. That network change influences density, compressibility, and the ease with which ions are shielded. It's a cascade where one property tunes another. What about surface tension? It stems from the fact that molecules at the surface have fewer neighbors. They hold tighter to the ones they have, creating a tautness. This is why raindrops are spherical. They minimize surface area, the costly skin. For plants, that skin helps draw water into tiny pores. For your lungs, too much tautness would pinch alveoli closed, which is why your body produces surfactants, molecular lubricants that relax the skin so breath can expand the canvas of life. The Grotthuss mechanism deserves another moment. In a chain of hydrogen-bonded water molecules, a proton doesn't cross the chain like a ball. Rather, the chain relabels which hydrogen belongs to which oxygen. Hydronium becomes water, and a neighbor becomes hydronium. Snap, 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 so the positive charge leaps forward. This is faster than a lone proton swimming. Inside enzymes and membranes, where pathways are lined with water and amino acids arranged like stepping stones, this leap becomes directed, efficient. That's why your mitochondria pump protons to build gradients, which then come rushing back through ADP synthase, a molecular turbine that builds the energy currency of cells. In the lab, we study water by looking at ultrafast spectra, laser pulses that ping the hydrogen bond network and listen to its echoes. We see vibrations relax in picoseconds. We watch orientations re-randomize. We measure how heavy water slows the dance. We also push water into crazy states, compressed in diamond anvils to gigapascals, heated in shock tubes to thousands of degrees. Each experiment is a question. Which of your quirks will reveal the underlying rules? And then there's culture. We treat water as mundane, sold in plastic, spilled carelessly. But the mundane is an illusion born of familiarity. Awe is not decoration here, it's the correct response to the architecture that sustains us. When you pour water from one glass to another, you're witnessing a fluid with memory-like correlation structures and network dynamics responding to gravity and boundary conditions with emergent elegance. Your kitchen is a physics lab. Cosmically, where should we look for life beyond the slogan of liquid water? We should ask, does the world hold a solvent with a high heat capacity to smooth energy? Does it form a floating solid to shelter life during winters? Does it have a high dielectric constant to stabilize ions? And does it allow a rapid mechanism for charge and proton transfer? Does it coax molecules into compact, functional shapes via a hydrophobic-like effect? On Europa or Enceladus, water may fill subsurface oceans warmed by tidal flexing. There, water could once again be the stage. On Titan, methane and ethane run the show at cryogenic temperatures. Life would have to write entirely new rules. It's fascinating, but the physics would be harder. No proton highways, weaker folding, slower reactions. One last metaphor to tuck into your pocket. Water is both the ink and the paper of life. Carbon writes the letters, proteins, lipids, nucleic acids, but water determines the fonts and the spacing. The meaning appears only when ink and paper meet. Before we end, let's revisit that floating ice and what it says about our place. In winter's first nights, when the surface of a lake begins to freeze, the coldest water, near 0 degrees Celsius, floats above 4 degrees Celsius water. The lake stratifies, oxygen from autumn winds gets trapped, nutrient layers form. Under the ice, life continues in slow motion. A small inversion in a density curve becomes a world-spanning mercy. And when you sweat after a run and the breeze cools you, your survival is paid for by water's huge demand for heat to evaporate. Your brain's temperature, kept within a narrow window, depends on that evaporation. On a larger scale, monsoons and hurricanes are orchestrated by the same latent heat, moving energy from the bulk to the sky, from equator to pole. The architecture of weather is written in hydrogen bonds. Now, synthesis. We asked, why does ice float, and how did that quirk save life? We found that water's anomalies, its rule-breaking, are woven from a common fabric, a dynamic, hydrogen-bonded network shaped by geometry and tuned by quantum effects. That network produces a density maximum that insulates lakes, an unusual heat capacity and vaporization heat that buffer bodies and climates, a strong surface tension and high dielectric constant that sculpt microscopic and planetary dynamics, and a self-ionization and proton hopping mechanism that make biochemistry quick and precise. Water's weirdness is not a bug, it's the bridge between physics and life. A contemplative takeaway. Tonight, when you pour a glass of water, hold it for a moment. Imagine the lattice of possibilities inside, flickering at 1,000,000,000,000 beats per second. Ask yourself, which of your daily rituals, remembering a name, catching your breath on a hill, watching a storm roll in, depends on this humble liquid's backlash against normality? Then try this thought experiment. If the liquid inside your glass suddenly became normal, if ice sank, if heat capacity dropped, if protons crawled instead of hopped, would the person holding that glass, the life you know, still exist in recognizable form? And the next great question. If water's properties are shaped by a hidden critical point and quantum touches, how far does this go in nature's design? If time is an illusion, what does that say about the memories we hold most dear, memories carried by ionic currents, stabilized by a liquid that itself lives on the edge of two states? In other words, what does water tell us not just about life's chemistry, but about the way reality permits continuity and change, about how the universe engineers the very possibility of a self? We'll go there next together.